we've got a function, a vector valued function, r of t, whose components are t squared and t squared minus t cubed. And the interval is in question goes from -1 to 1. That's the time interval. So this is f of t, and this is g of t. Let's do both what we can by hand and Mathematica. This is, again, the standard way I'm going to want you to do things. So f of t is t squared, g of t is t squared minus t cubed. Go ahead and enter r of t as a vector, but you've got to use curly braces. Once f and g are defined, I can do it this way. Go ahead and define the velocity vector right away. And one thing new in section 11.3 is our textbook author starts calling these things velocity vectors instead of just the derivative of the position vector. All right, in section 11.3, the main new emphasis is to relate it to motion in the textbook. That's the main purpose of all this. That's the main outside application, is to motion. For the sake of doing it, I think I'll add the acceleration vector in there as well. That's worth doing, and that comes up in section 11.3 as the rate of change of the velocity vector. And we want to start trying to today understand the acceleration vector. In particular, we want to start to get a little intuition about how it's related to the velocity vector. It is its rate of change. It is its derivative. We want to understand that intuitively. We'll have Mathematica computed, but let's see what we can compute by hand. The velocity vector, v of t, is r prime of t. In the general case, that's f prime comma g prime as a vector in 2D. And for our example, that simplifies to 2t comma 2t minus 3t squared. The acceleration vector is the derivative of the velocity vector. And yes, you could also say it's the second derivative of the position vector, as you would expect. In terms of f and g, the components will be f double prime of t and g double prime of t. And in this example, that will simplify to 2 comma 2 minus 6t. These things are functions of t. We can evaluate them at any value of t that we want and try to interpret the meaning of these at different values of t. But what's most insightful is thinking about letting t change and seeing an animation, seeing how these things change over time. I've also mentioned the speed. Speed being different than velocity, it's the magnitude of the velocity. And this mathematical definition really does correspond to physical meaning of speed. Like if you're in your car, making a Lissajous figure in a parking lot, okay? Whatever your speedometer says, that's the speed, right? Your speedometer doesn't know what direction you're traveling in. You know what direction you're traveling in, you can see it. When you combine the speed information with the direction information, you can tell what direction you're going in, whether you are actually watching yourself as you drive, watching the road, or if you got a drone hovering above you and filming you as you drive, you can reconstruct your velocity vectors as well, taking the directional information into account. But the speed really is the length of the velocity vector. And essentially by the Pythagorean theorem, that's the square root of f prime of t squared plus g prime of t squared. It's the Pythagorean theorem. That's one way to derive the speed. Another way to derive the speed is to think about the distance traveled and differentiate that. And you do get the same answer either way. But the distance traveled has to be computed as an integral of this magnitude. So it seems a little like you're going in circles, but they are related. Essentially, it's the fundamental theorem of calculus. This is also, and this is worth knowing, the square root of the velocity vector dotted with itself. Right? Because the square root, the magnitude of any vector is the square root of that vector dotted with itself. That is worth knowing. I've also mentioned it's worth knowing the equation that you would get when you square both sides. The squared magnitude of any vector, I'm writing the velocity vector here, but this is true for any vector, is the dot product of that vector with itself. That's a formula worth knowing, including in a conceptual point I'm going to make today. So for our example, this simplifies to what? Gotta find the square root of the sum of the squares of the components of that vector right there. There's the velocity vector. First component 2t. That's got to get squared. Second component 2t minus 3t squared. I have to add the square of that. Integrating this speed is probably not going to be simple. Probably it's going to have to rely on numerical integration. It's probably not doable symbolically, I'm guessing. But let's simplify this anyway. 4t squared plus, if I FOIL this out, I'll get a 4t squared and a minus 12t cubed plus 9t to the fourth, it looks like. Continue simplifying. The speed simplifies to the square root of 9t to the fourth minus 12t cubed plus 8t squared. If I were going to try to integrate that by hand to find the distance traveled, it might be worthwhile to factor out a t squared like this. Oops, that's to the first power. That's a 1 there. I didn't need to write it at all. And then the square root of t squared is technically the absolute value of t. Though when t is positive, I can get rid of the absolute values. When t is negative, I can't. And I am actually allowing t to be negative here, so I probably should keep the absolute value signs in there. Maybe I'll write it as a piecewise function. This is t times the square root of 9t squared minus 12t plus 8 when t is greater than or equal to 0, and negative t times the square root of 9t squared minus 12t plus 8 if t is negative. But, if t is negative, the negative t is positive. The speed is still positive. And I'm glad I did this, because now it is telling me that maybe integrating this would be possible by hand. I mean, it's not a slam dunk. Trying some substitution like u equals 9t squared minus 12t plus 8 might work. I mean, it's an extra complication of this t term makes it an extra complicated, but du is almost there. If you're going to try to integrate by substitution, it might be possible to do by hand, and we'll have Mathematica try it. But it is true that the distance traveled, you could call it dist of t, also known as arc length, is the integral of the speed I'm telling you general principles here that are in the reading. But be careful how you write this integral. I'm really a stickler for writing this in a real precise way that many science and engineering professors don't. First of all, write the starting value of time, in our case, -1, as the lower limit of integration. So we are starting time at -1 instead of 0. Yes, kind of an odd thing to do, but technically doable. Make the upper limit of the integral the t. Make those match. For the variable of the function that's being integrated, don't call it t. Call it something else. What? Well, anything you want except t. U, v, w, x. I'm going to use a Greek letter tau, the Greek version of t. Tau d tau, right? I like using Greek letters whenever we can here, because they're just so pretty. Make it different. Why? Because you really want to emphasize the true variable for this function of t is that upper limit of the integral. As t changes, it's changing that number up there that affects the value of this function. Yes, the speed is a function of tau. If you made the graph with a tau axis here, that affects the answer, but you're really letting the right endpoint of the interval change. That's what's really changing to affect the value of the function. And when you write it this way, it's also worthwhile to emphasize the fundamental theorem of calculus would imply that if you differentiated this distance function with respect to t, you would get the speed function at that value of t. Don't put a tau there. In the calculus book that we use here at Bethel for Calc 1 and Calc 2, you'll find the version of the FTC that I'm using here in chapter 6. It's called the second fundamental theorem of calculus. Boy, mathematicians are so inconsistent sometimes. In other books, they sometimes call it the first fundamental theorem of calculus. I'm differentiating an integral. It's not the most common way to use the fundamental theorem of calculus, right? What's the most common way to use it? The most common way is you're trying to do an integral, trying to integrate a little f, and you find a capital F, antiderivative, and you do capital F of b minus capital F of a. That's the most common application of the FTC. Chapter 5 in our textbook for Calc 1 and Calc 2. This is different. We're differentiating an integral where the variable's up there. You'll find it in chapter 6 of that book. 6.4 is the section. It's a worthwhile thing too, because it emphasizes you can use integrals to define antiderivatives, even if you can't find a nice formula for them. I'm serious. I'm very, very serious. It emphasizes you can use integrals, thinking of them in terms of areas under graphs, to define antiderivatives, even if we couldn't actually do the integral, even if we can't actually integrate this thing, it's still a definition that makes sense. And it can be approximated with numerical integration technology. And this is still true. And you can make graphs of these things to verify this, as we will here in a minute. Let's do that now. So I'm emphasizing both calculations and concepts at the same time here. Probably the best way to define the speed in Mathematica is using a dot product, actually. Do the speed as a square root of v of t dotted with itself. That's how to do a dot product. Where'd that dot come from? That's the period button, not a star. Don't do a star. Make a note to yourself. Don't do this. Do this. Period in Mathematica does dot product, not star. Is it the right formula? It's unsimplified there. Let's expand it. It's not expanding for some reason. simplify. That's not as simple as I was hoping. Well, okay, it is factoring out the t squared here like I did there. I did get the right answer. Is this easy to integrate with some symbolic technique? If I type this, will I get an answer? I don't know for sure. Let's see what happens. Right. Oh, that's not what I wanted to do. Speed. Okay, I guess it's possible. Yikes, though. Are we happy? We can do numerical integration with whether with Mathematica or a calculator or something else, maybe MATLAB. And Mathematica does it symbolically too, if we really wanted a symbolic answer. Sometimes it makes answers that look different than if you put the integral in other forms. Like if I integrate, say, this piece, it might look different. Let's see. T times the square root of 9t squared minus 12t plus 8. It is looking a little different, okay? I mean, there's similarities. There's logarithm in there. By the way, log, if you didn't remember, does mean natural log, actually. When you get high enough in math and physics, grad school level, mathematicians and physicists go back to using log for natural logarithm. Why? I think I asked a professor once. I don't know for sure the real reason. Maybe it's because this professor said, well, that's the best logarithm to use anyway, so why not just call it log? And Mathematica's author is Stephen Wolfram, who's a physicist, so that's why he did that. Maybe it's biased against the French. You know, ln is French. I can't speak French, so I'm going to get the pronunciation mangled. But it's like, ln is like log natural. Okay, imagine I said that in French with a good French pronunciation. Maybe it's biased against the French. I don't know. Anyway, I guess it's possible. Could I do it by hand? Maybe. I'm a little scared to try, but well, okay, I could try, but I'm not sure how easy it would be. Is this the distance traveled function, or maybe this? Let's plot it and see if it seems like it could be the distance traveled function. Probably it's not, to tell you the truth, because probably its value at t equals -1 is not 0. And in fact, it's even weirder. It's discontinuous. How could that be? Yeah, some weird stuff's going on here. In reality, this is not what we want. So sometimes the technology can lead you astray. I'm guessing it's sort of having a difficult problem dealing with what's going on in t equals 0 and the change in that happened from the absolute value function. And it's doing something I don't want it to do. So probably because of that, it's better to define the distance function with the technology numerically. How? How about like this? This will be the thing we want to do in general, actually. N integrate. That means numerical integration. And you don't even have to program it yourself. It's a built-in function. You don't have to do Simpson's rule or something like that. It's doing Simpson's rule for you, or maybe something even better. Speed of, okay, you do want to use a different letter here, like a tau. How to make the tau? I did escape T, oops, no, escape T escape. It's also on the palette somewhere. Search through there, you can find a tau. You don't have to use a tau. I just like using it. This is effectively integrating the speed from, oh, not 0, but -1, sorry. From -1 to t. That's the syntax. But it's doing a numerical integration. It's doing Simpson's rule for any value of t that you want. So for example, over the entire interval from -1 to 1, the distance traveled is about 3.3. over the interval from -1 to 0, the distance is about 2.2. From -1 to -1, you haven't traveled any distance, 0. Let's work now on understanding what all this means. First thing we could do, as quick as possible here, I've already showed you this last time, is make an animation where we show some graphs. We have Mathematica is based on nested functions. Manipulate is going to animate whatever is inside of it, so to speak. The show will combine different graphs. What kind of graphs? I'm going to make a parametric plot. I'm also going to use the graphics to make some arrows. So those are different kinds of commands that make graphics that are going to be combined with show. That's the idea of what's going on here. So there's parametric plot. By the way, the little red carets are saying, hey, I want more input there, but I'm leaving that input for later. Graphics will make the arrows. Generally speaking, it's best to build this up piece by piece and maybe try the parametric plot first, make sure that's working before you add the graphics with show. But I have enough experience with this that I think I can do this all at once without making a mistake, hopefully. What am I plotting with parametric plot? I'm plotting the parametric curve, R of t, comma, over some interval. T goes from -1 to 1 in the end, but if I want my animation parameter to be in there to make an animation, call it B, that's going to be the right endpoint. Over here, right before the last square bracket, I put a comma, and I put my animation parameter inside curly braces, starting just barely bigger than -1, -0.999, say, going up to +1. I do know from experience that I better put a big plot range in here to keep that steady, like I showed you last time. What's this going to look like? F of t is t squared between -1 and 1. That's going to vary between 0 and 1. It's a parabola as an ordinary graph. G of t is this thing. What's the graph of that going to look like? That kind of cubic. And between -1 and 1, g of -1 is what? 1 minus, like 2 maybe. G of +1, 0. Yes, it's not going to, we're going to be pretty close to the origin is what I'm trying to say in all this. A plot range, like say going out to 5 in all directions is probably good enough. That's shorthand for going from -5 to 5 in the x direction and -5 to 5 in the y direction. Inside the graphics, I need curly braces. I want to make my arrows, my position vector, my velocity vector, and my acceleration vector. Going to make them a little prettier this time. Colored with some thickness to them. Say thick, maybe even thickness. I like making my position vector blue. Starts at the origin, goes out to R of B. Maybe I should enter this as is right now, and then I'll make updates. So what we should see here now is the curve with the position vector colored blue. I thought that might happen. It does have the unfortunate effect of not always having the origin where it should be. So it's changing the origin location. That can be fixed. Maybe after the plot range type, comma, axes, origin, arrow, 0, 0, or it should be. There we go. There's the motion. Now you might want to zoom in closer there, and maybe I will. Though that does sometimes run into the trouble of the velocity vector and acceleration vector being really long. Let's zoom in closer anyway. 3 here. I'd like to make the head of the arrow bigger as well. Arrowheads, let me try 0.1. It might be too big. So that's the position vector. Make the arrowheads a little smaller. Now I want to add velocity vector and acceleration vector in there. So after this arrow thing right here, I'm going to put another comma, red arrow. My velocity vector, don't start at the origin, start at R or B. I'll put 0, 0 there first. End at the tip of V. When I put that base at R of B, I need to effectively do R of B plus V of B here. There's the velocity vector. And it is kind of long. Though I do remember the motion slows down as you approach the origin, so it gets shorter. It does some kind of funky things near the origin there. That's just an artifact of Mathematica and how it does things. It like switches the direction around in weird ways. And then let's add the acceleration vector too. And make it, how about magenta? I always think of that. I always think of Blue's Clues whenever I say the word magenta. Never when I say the word blue, though. Okay, so the acceleration vector is kind of long, pointing in the other direction. It does get shorter, I think, as we go in here. Yeah, now you can see it. Since that one's so long, let's scale it down by a factor. Let's try a factor of 5. So I'll divide this by 5. Okay, so now you can see it's barely in the picture. That's the acceleration vector divided by 5 in length. All right, so what are we seeing here? We want to understand now. So the position vector always points. Let me add one thing to this picture. Sorry. One more thing. Maybe right here. Black, point size. Let's put a point for the location of the object. There it is, that dot. There's our particle. Okay, so the particle's moving. As time goes by, it's tracing out a curve, a parametric curve. The blue vector, the position vector, is just keeping track of where the particle is at every moment in time. But as an arrow, it is changing. It's changing both in direction and magnitude in a smooth way. It's got a rate of change. It's got a derivative measured by the velocity vector, the red vector. What we saw last time, we didn't prove, but we gave it intuitive argument for the fact that that velocity vector is always tangent to the curve, if you draw it in the right spot at least, and pointing in the direction of motion, and having a length equal to the speed. So when you're going slower, as we approach the origin, we go slower, the velocity vector is getting shorter, the speed is getting smaller. Once we pass through time 0, we go through the origin. Evidently, at time 0, we kind of stop. There's a cusp here. This is one of those non-smooth examples. The velocity is 0 at a point, at t equals 0, in fact. If you plug in t equals 0 here, you get 0, 0. I don't know if you've done the reading well enough to remember that when the derivative of a differentiable vector valued function is 0, we say it's not smooth there. And that's kind of like why we've got a cusp in the graph. At one moment in time, t equals 0, effectively the motion is 0. The velocity vector and the position vector in this case, for that matter, are both 0. The acceleration vector is not 0. It's not that the derivative at 0 doesn't exist. It's that it equals 0, and that leads to quite often there being cusps in the motion in the graph. Not always, but quite often. We continue on, and now we move away from the origin faster and faster. The velocity vector is getting longer and longer. The pink vector, the acceleration vector, what's going on with it? It's the rate of change of the velocity vector. What you want to imagine, this is what the author emphasizes in the reading, is that pink acceleration vector kind of pulling on the red velocity vector. You can see here they're pointing in almost the opposite directions. What that means is it's telling the red vector to get shorter and not change direction very much because they're almost parallel. So as we move in, increase time a little bit, the red vector continues to get shorter and not change direction very much. As we get close to 0, it still gets shorter because the acceleration vector is pointing in the opposite direction and not changing direction very much. You got the weird thing going on at 0 that's hard to describe. But ultimately, as we continue going on here, now the acceleration vector, the pink one, is pointing in the general same direction as the velocity red vector. Their dot product is positive, in fact, telling the vector, so to speak, to get longer, to speed up. And it's also pointing more downward there, you can see. So that's kind of effectively telling the red vector to rotate now. Clockwise, in fact, because the pink vector is pointing downward. It is, in that intuitive kind of way, not precise way, affecting how the red vector changes. It is the rate of change of the red vector. Some other kinds of concepts that you were asked about in the homework due Friday includes things like figuring out where the speed is minimized. Yes, we can make an ordinary graph, a regular plot of the speed. Notice this is the speed, it's not the velocity. The velocity is the vector. I can't make a regular plot of the velocity. There's the speed. If I tried the velocity here, I'd get an error. Or I get two functions because Mathematica thinks it wants me to graph two functions. But that's not right. I'm trying to graph the speed. That's how the speed graph depends on time. And notice it looks like it has a point that's a cusp at t equals 0 as well. It's not a guarantee that that'll happen when the speed is 0. It happens in this example. So the speed is minimized at t equals 0. So you, in a general problem, to minimize the speed, it's a matter of trying to minimize that function. Hey, with Calc 1 methods, take its derivative, set it equal to 0, solve for t in general. Got a square root in there. That doesn't sound so pleasant. You can minimize the speed by minimizing its square. So instead of minimizing the speed, you can minimize this function. You can take its derivative with respect to t, set it equal to 0, and solve for t. This is 0 when t is 0. The speed is minimized when t is 0. The critical point is t equals 0. Is it minimized where this is 0 as well? Possibly, but I'm guessing that that thing probably has complex roots. Is that true? Yeah, the imaginary unit there. Complex number roots. So the only real solution for where this is 0 is t equals 0. That's the only real critical point of the speed function. And that is where it's minimized. And the minimum of speed in this case is, in fact, 0, but that's not always the case. Sometimes the minimum value of the speed is above 0. But the bigger point here is you can minimize it by minimizing its square, so you can get rid of the square root if that comes up in a homework problem or an exam problem on Monday. Can you plot the distance traveled function too? Plot speed and distance. Sure, but it's a little slow. I'm going to answer this. It's going to take a few seconds. Because it's doing, I don't know, hundreds of numerical integrations. That's why it's slow. Okay, it wasn't too bad. It only took about 2 seconds there. Sometimes it takes longer. Doing hundreds of numerical integrations there because it used n integrate. This orangish graph, that's the distance traveled. Notice dist at -1 is 0. The derivative of the orange graph, the gold graph, is the blue graph. If you want to know the slope of this gold graph, it's the value of the blue graph. The slope right here at t equals -0.833 is close to 4. That's the slope of this graph right here. Rate of change. Slope is 0 right there. Value of the speed, its derivative is 0. Slope becomes positive over here. The speed becomes positive. The distance was defined by the integral, and yes, its derivative is the speed. And this function does give you the distance traveled at any moment in time, starting at time -1. And like I said before, you can find its value at any moment in time if you need it. The total distance traveled is about 3.3 along that curve from -1 to 1. Probably a final thing worth emphasizing today. Well, okay. Couple final things worth emphasizing. So the integral of the speed of the distance traveled. What happens if you integrate the velocity vector itself? This comes up on the homework too. If you integrate the velocity vector itself, does that have any meaning? Yeah. It's the displacement. It's the change in position. This is delta R. R of B minus R of A, which could be 0. Would be 0 if, for example, was a bug flying around, starting here at time 0 and going all over the place, coming back to where it started. The velocity is never 0. The speed is never 0, but somehow that integral is 0. That can happen. Effectively, positives and negatives kind of canceling out, so to speak, to give you a displacement of 0. So that's one important conceptual point to mention here in the last few minutes. Another important conceptual point is this one here, key idea 11.3.1. If an object moves with constant speed, so the length of the velocity vector is the same always, but its direction could change, then the velocity and acceleration vectors are orthogonal, which means perpendicular. The dot product is 0. This is related to a fact that was in the reading from last time, that if the magnitude of a vector, a more general fact, if the magnitude of a vector is a constant, then that vector and its derivative have a dot product equal to 0, meaning they're orthogonal. And I want you to understand this derivation that I'm going to do in 30 seconds here now of this. Call this constant C. If R of t is always equal to a constant C, then R of t, the magnitude of that squared, is also equal to a constant, the square of the original constant, which means R of t dotted with itself is constant, which means if you differentiate both sides, if you differentiate this dot product, you got to get 0 because the derivative of a constant is 0. And this derivative by a product rule from the previous section, which we didn't have time to talk about in class, but came up in your homework. This is r of t dotted with r prime of t plus r prime of t dotted with r of t. That's a product rule, effectively. And that equals 2 r of t dot r prime of t. So what you effectively have is this is 0, and therefore dividing both sides by 2, this is 0. So in any situation, if you've got a vector valued function whose magnitude is constant over time, it and its derivative will be orthogonal, perpendicular. In the case where r of t is a position vector, then you're saying the position vector and the velocity vector are orthogonal. In the case where r is a velocity vector, then you're saying the velocity and the acceleration vector are orthogonal. That's what this is saying. And constant speed motion is a common situation to model because it's fairly simple.